As a hobby, I like to read and answer various statistics and data science related questions I come across on the internet. One of the most common statistics questions I come across online is some variation of, how can I test if my data is normal, or how do I make sure my data is normal? Normal here referring to the normal distribution, also known colloquially as a bell curve, or maybe a Gaussian curve if you're from a scientific background. Most of the time, whoever is asking one of these questions doesn't need to make their data normal since it's not relevant to what they're doing. I don't see many cases with these questions where normality is required, maybe because those are posted elsewhere, or maybe because there's some self-selection bias where individuals who are more likely to understand these tests are also more likely to understand where they're needed. In the rest of this video, I will discuss what the normal distribution is and when it is needed, common scenarios where you don't need variables to be normally distributed, why requiring true normality in many cases is a bit of a fool's errand, and a few ways to make your data normal if it still requires it. Now, before I imbue this video with any more cynicism, let's get back to discussing this distribution so that we know what we're working with. The normal distribution is one of the first probability distributions that students learn in an introductory statistics class. This equation defines the distribution, but all you need to know is that we use Greek letter mu to describe the center and mean or average of the curve, and Greek letter sigma squared for its variance, which is proportional to how wide it is squared. It starts off sort of flat in the middle, then starts to fall down on both sides like a roller coaster, and it tapers off close to zero very quickly after that, also kind of like a roller coaster at the end of a ride. We can also simply write n of mu sigma squared to describe the same distribution, although we don't plug in values of x here. It's kind of like saying square root versus writing square root of x with x written in it. The equation itself might scare some people, but for most students, it's just something you plug into a calculator or a program like Microsoft Excel, Python, or R. You may have noticed that I defined sigma squared as the variance, but not sigma. Sigma by itself is a standard deviation and is useful and usually more intuitive than variance. For example, 68% of the area under a normal distribution, that is 68% of the probability, is within one standard deviation of its mean on either side. 95.4% is within two standard deviations and 99.7% for three. If you've ever seen the margin of error of plus or minus some percent in polling numbers, it usually refers to the region within 95% of the estimate, which is just slightly under two standard deviations. The normal distribution also has many properties that make it useful to work with. For starters, if you add two independent normally distributed variables, you end up with a new normally distributed variable, and its new mean is the sum of the original means, and its new variance is the sum of the original variances. Similarly, you can multiply or divide a normal distribution by any number, and the result is a normal distribution with its mean multiplied or divided by that number, and its variance multiplied or divided by the square of that number. For example, doubling a normally distributed variable with mean 10 and variance 4 would result in a new one with mean 20 and variance 16. There are some more properties of the normal distribution I will discuss later, when relevant, but for now, I would like to highlight the three most common cases where someone in an introductory statistics setting might be interested in making sure data is normally distributed. Okay, so the first scenario that a student in an introductory stats class would want to make sure a variable is normal in is when performing what's called a z-test. The purpose of a z-test is to compare the mean of a normally distributed variable with a known variance to a fixed value, or possibly the mean of another normally distributed variable whose variance we also know. Essentially, what we want to know is if we consider one value to be less than, greater than, or maybe just not equal to another value. Also, a forewarning, this is going to be the densest section for math in this video. After this, it should be pretty smooth sailing. Anyway, the z in z-test refers to a standardized test statistic, z. Standardizing, at least in this case, involves two steps. 1. Subtract the mean from the distribution. This ensures that it is centered around 0. And then 2. Divide by the standard deviation of the distribution. This results in the new distribution having a standard deviation of 1. If we have more than one data point, we can describe the distribution of a sample of n points by using two equations we saw in the previous section. First, we can describe the average of a sample using x with a bar drawn over it, also called x bar. X is the data, Bar means you divide by the sample size. It is essentially n different normal distributions that we can add together, and the distribution of their sum is also normal, with mean n times mu and variance n times sigma squared. Then, we can divide that distribution by n, which results in a normal distribution with mean mu and variance sigma squared divided by n, which means it has a standard deviation of sigma divided by the square root of n. One way of looking at this is if you want half the uncertainty with a sample of numbers, you need 4 times as much data, since the 2 1/2 is the square root of 4. We can plug x bar, mu, and our new value of sigma over the square root of n, into the above equation to calculate our z statistic. Then you can look up its corresponding cumulative probability in a table in a book, or just plug it into a program like Microsoft Excel, Python, or R. As a quick side note, I will have a link in the video description to documents on how to calculate these statistics and others in this presentation in Microsoft Excel, Python, and R for anyone who is interested. As an example of where this test might be used, say you wanted to see if students at a school underperformed an SAT test by using a small sample. The national average is 1060 with a standard deviation of 195. If you randomly sampled 10 students and got an average of 950, you could plug that mean into the equation, yielding a z-value of negative 1.78. We can plug negative 1.78 into a program like R, which shows that it has a one-tailed p-value of 0.037 or 3.7%. This basically means that if the students of that school had the same mean and standard deviation as the general population, there would only be a 3.7% chance of having a random sample of 10 students having that low of an average score or worse, and we would probably assume that students from that school are underperforming on the SAT. You can also see how the purple dashed line in this graph, representing the mean of the sample, is on the left tail of the red curve. The red curve represents the distribution of the average of random samples of 10 students nationally. Meaning, if you kept taking random samples of 10 students, you would expect the averages of those samples to follow the distribution represented by the red curve. Alright, I'm going to need to take a brief pause here to describe one of the most important concepts in statistics and the metric for evaluating most of the tests in this video. P-value. 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 P-values. That 3.7% chance I just mentioned is an example of a p-value, which is the probability that you observe a result at least as extreme as you did if your original assumptions, aka the null hypothesis, are true. Usually you only test one of the assumptions, and the rest are taken for granted. In this case, we tested that the mean was not below average, but we also assumed the normality and the standard deviation of the distribution. And, because we were only concerned with scores being on one particular side of average, below average, our extremeness was just how far the average score was below the top score. It might help to just think of the p-value as a surprise value, where the lower it is, the more surprised you would be if all the default assumptions were true. For reference, 5% is commonly used as a cutoff for rejecting a null hypothesis versus failing to reject it. It doesn't definitively prove anything, but it's often treated as close enough. Compared to what students learn in class, in practice, the z-test is not extremely useful because the variance of the distribution isn't usually known in advance, and by estimating it, you change the assumptions of your test. In fact, in the previous example, we assumed that the standard deviation of the students' scores in that one school had the same standard deviation as the national average, which is extremely unlikely. These assumptions can be relaxed, however, if we use t-tests. Normally distributed data with unknown variance can be compared, but we're going to need to use a different but closely related type of test called a t-test. The estimate for t, the test statistic here, is almost the same as estimating z, except we use the sample standard deviation instead of a known one. When we estimate the variance, we use the formula for sample variance, s squared equals sum of x minus x bar squared, over n-1. And yes, the n-1 isn't a typo. I generally don't like hand waving like that, but the reason why it isn't n involves a decent bit of math, including calculus, so we'll avoid that for today. The resulting distribution for the t-statistic is a bit wider than a normal curve. It is analogous to the standard normal curve, except it has a parameter called degrees of freedom, which is nebulously its effective sample size. For a single sample, or for paired data, the number of degrees of freedom is n-1. For two unpaired samples, there are other methods we won't worry about today, but I recommend looking up Welch's t-test if that is something you are interested in. Let's take a look at an example of how the t-test might be used. We give 10 people a sample of coffee A and coffee B, and they rank each on a scale of 1 to 100. Here, the actual sample is just the differences between coffee B and coffee A for each person, so we can treat this like it's just a sample of data with one variable. We estimate the mean and sampled standard deviation, 15.9 and 18.2, and we can calculate our test statistic t with 9 degrees of freedom. In this case, we are interested if one is greater than the other, so we will use a two-sided test. We measure from the center 0 and set our p-value threshold from 5% to 2.5% on each side, since 2.5 times 2 is 5. In this case, it looks like they are significantly different, with coffee B having a higher average score, so we would assume that coffee B is preferable to coffee A. One important fact about the t-distribution is that as the degrees of freedom approach infinity, it gets closer to being a normal distribution with mean 0 and variance 1. The implication of this is that with a large enough sample, you will basically get the same results using a t-test or its analogous z-test. On to the last example of a case where data should be normally distributed. Linear regression. Specifically, in ordinary least squares linear regression, or OLS for short, we are trying to fit points to a line, and the points should be normally distributed above and below that line. The differences between the points in the line are called residuals, which are like errors you get from fitting the data. OLS models look something like this, where you're fitting y, which is the sum of a constant value, aka the intercept represented by beta 0, a bunch of other beta values multiplying the independent variables in the model, plus normally distributed noise. The model could be something like this formula for calculating housing prices, where the average housing price is $4,000 plus $100 per square foot, plus $20,000 if it has a pool, with a normally distributed error term having a standard deviation of $5,000. So most houses will fall within 2 standard deviations, or roughly $10,000 of the estimate you'd get from this equation. The way the model is fit is by minimizing the squared error of the data it's training on. This can mathematically be done multiple ways, using linear algebra or calculus, but is beyond the scope of this video. At the end of the day, though, the fit is based on the error terms being normal. So, as a quick recap, z-tests, t-tests, and linear regression residuals are the 3 most common scenarios in which someone with an elementary knowledge of statistics would want to ensure that the numbers they see are normally distributed. Now, I will discuss a few scenarios that don't require normality. We'll start by continuing the discussion of linear regression, as it is the most common case that I see. I was originally going to make this section longer, but in the interest of time, I'll just reiterate. Only the residuals and errors of a linear model need to be normally distributed. Independent and dependent variables can be whatever. Non-negative integers like age? Fine. A binary indicator that is 1 if you have a mustache and 0 if you don't? Perfect. You usually want your dependent variable more or less continuous, and to use a different type of model otherwise, like logistic regression for categorical data, or Poisson regression for certain count data. I guess I'll just leave this message here. discuss the more general reasons why you don't usually need data to be normal, even in those previous scenarios. One of the fundamental theorems in statistics, the central limit theorem, states that if you take the average of a large sample of independent, identically distributed data, the distribution of that data will approach a normal distribution with the same mean as the distribution of the data, and the variance equal to the variance of the underlying distribution divided by the sample size. Basically, what this means for us is that if you have a large enough sample, which in practice usually ranges from 20 to 50 data points, you don't need to worry about the data being normal for t-tests. As a couple examples, take a look at a mixture of two normal distributions and this gnarly beta 1/2 distribution. They are clearly not normal, yet when you average more and more points together, the distributions of their averages become normal. This doesn't work for some distributions with infinite variance, like this Cauchy distribution, f of x equals 1 over pi times 1 plus x squared, but you probably won't encounter actual sample data distributed like that in practice. At the heart of the problem with expecting data to be normal, it doesn't really occur in real-life examples. There's always some deviation away from normality, whether a result of the shape or precision of the data, like rounding to dollars or cents with money, or because it is just some other shape that might be very close to normal, maybe because it has a minimum or maximum value, which a normal distribution does not have. Tests for normality, like the Lilliefors test, will inevitably reject the null hypothesis of normality with a sufficiently large sample size, even if the data looks normal to the naked eye. In the case of this test specifically, it looks at the maximum difference between two cumulative distribution functions, or CDFs. A CDF has a range of 0 on the left side to 1 on the right side, and basically represents the cumulative probability that a point sampled from a distribution is less than or equal to a particular value. Essentially, for the Lilliefors test, one estimates the mean and variance of the data, and then compares it to a normal distribution with the same mean and variance. Specifically, it uses a test statistic that is a maximum absolute difference between the two distributions. Since the last couple of minutes have been a bit dry, let's use more exciting, real-life data. Here I have 47 non-wet chickpeas that I am weighing on a scale. You can see the approximate weight distribution with 25-gram bins, alongside a normal distribution with the same mean and variance. We can plot the empirical CDF of the data alongside the CDF of the normal distribution, noting it looks like a dangerous staircase. Scanning across the graph, we can see the absolute difference between the two curves go up and down, with the red line indicating how far apart they are, and the pink showing the maximum difference up until that point. The maximum difference, our test statistic in this data, is 0.0622, which we can plug into the Lilliefors test, which produces a p-value of 0.92. That's a word for it. Okay. Well, I guess chickpea weights are kind of normally distributed then. Regardless of the p-value you get, looking at the test statistic itself gives you a rough idea of how far away the distribution is from a normal distribution. Small value by itself, regardless of p-values, might be enough proof for you to call something close enough to normal. Similarly, you can use a quantile-quantile plot, or QQ plot for short, to visualize the CDF of your data with a theoretical one on x and y axes, and you can just make a judgment call with your eyes. If the data is mostly along the line, you are probably fine, and this is, oddly enough, a fairly reliable test. As for other tests, you can also run the Shapiro-Wilk test if you want a reasonably powerful one. It's arguably the best out-of-the-box test for samples of up to 5,000 points, and the Anderson-Darling test can be used for larger samples. You should be able to find either on an internet search with those names plus your analysis software of choice. Unfortunately, there's no good metric that can describe a set of distributions that is close enough to normal. Most of the time, if normality tests won't tell you what you ought to do, you can either use your judgment, or you can run simulations if you think it would have a noticeable impact on your analysis or model. So, if you've gotten to the point where you think non-normal data is a problem, there's commonly one issue with trying to correct it. It's often important to keep your data easier to interpret, and changing it to make it normal would make it unintuitive and maybe even inflexible to use for other purposes. Sometimes, though, it can be the correct call. I will focus on transforming the data in this final, upcoming section. Before I proceed, I would like to mention one other common source of non-normality that I will not focus on: outliers. Outliers are a small amount of data that are very far to the left or right of most of the data, and are often encountered in modeling and data analysis in general. The methods of dealing with outliers can get quite specific and are highly context dependent, but as a piece of general advice, unless you think they are incorrect measurements, you should probably keep them or limit the scope of your analysis to not include such data. Or maybe they're more reasonable after the data as a whole has been transformed. Back to linear regression. If you are stuck with obviously non-normal residuals in your model, the best approach is to often just improve the model itself with adding or removing independent variables and possibly transforming them. You might see this if you plot a variable versus residuals and see some sort of pattern, like with this toy example here, where there's an obvious curve that looks like it could be quadratic, and we could try adding the square of that variable into the model, which, as you can see, solves the problem. Variable selection and transformation is a very broad topic, but it is arguably the best way to resolve issues with normality and linear regression. Speaking of transformations, for linear regression, one of the most commonly used ones is the box-cox transform, also known as a power transform, which looks like this: y to the power of lambda minus 1 over lambda if lambda is not equal to 0, and natural log of y if lambda is equal to 0, where lambda is the transform parameter. Basically, you are raising a non-negative value y to some power with an offset of 1 and scaling it. This could be something like squaring values with lambda equal 2, or taking the square roots of them with lambda equal 1/2, but the actual value of lambda used can be somewhat arbitrary. The scenario that I've usually seen this used in is transforming the dependent variable of a linear model so that the residuals are normal when being fit, but it can also be used on any numeric data, with some restrictions or adjustments needed on negative values. For the box-cox transform, you normally choose a range of lambda values to check, and then select the one with the best fit by finding the one with the highest log likelihood. The likelihood is the product of all the probability densities of each data point, in this case, the residuals. Taking the log makes it easier to calculate and doesn't change the outcome, but at the end of the day, you're just looking at how many times more likely one outcome is than all the others, all else equal. Oftentimes, if this is a transformation I'm considering, I only look at the log transform case where lambda equals 0, since the interpretation of that model is that individual variables have a multiplicative effect rather than an additive effect, as you can see by just taking the exponential of both sides. This is somewhat easy to explain to a general audience versus the other transforms, like spending an extra $1,000 will increase sales by 10%, rather than increasing the square root of sales by 5. An example of where I did this is when looking at the best time to post on Reddit almost a decade ago. I built a model using a bunch of input variables, including the web domain of posts, time of day and day of week, and the target variable was log of 1 plus score, setting scores below 0 to 0. Technically slightly different than a log transform, but again, close enough, works pretty well in this case too. You can see the different times of day and week that have higher scoring posts, as well as the domains that are best for getting more upvotes, which were primarily image hosts. You can also apply the transformation to different independent variables, but if you try testing various transformations willy-nilly, you run the risk of p-hacking, which can result in an overfit model by random chance. An analogy to p-hacking is, if you throw a handful of marbles across a room a million times, chances are they're going to line up at least one of those times. One of the most common solutions to this problem is validating a model's parameters using a validation set alongside the training set and measuring the final error on a test set. Basically, you want to avoid overfitting configurations, sometimes called hyperparameters, like which variables to choose or how to transform them, when trying out a large number of them. So, you train each on a training set and then see what kind of errors you get on a set you didn't train the model, the validation set. Then, you want to present a realistic outcome, which is based on whatever error metric you use, so whichever model works best on the validation set, you run it on the test set to report the error. At this point, you can use the model you already trained, especially if training is expensive, or you can train a new model on the whole dataset to take advantage of the full sample size. There's no strict rules on how to divide up your whole dataset into train, validate, and testing sets, but for smaller sets, you want at least 50% of your data to be training, and for larger sets, you might be okay with something like 99%. Alternately, you can use cross-validation, where you still have the test set, but the train set is divided into n different parts that each take a turn being the validation set. So you just end up averaging, say, 5 or 10 different validation errors for each configuration, which takes several times longer to run, but can be more effective. Seriously, if you have a reasonably large data set, I cannot stress enough how effective this technique is for model building in general. Regardless of what method or transformation you choose, you should prioritize best statistical practices and avoid overfitting a model. Ultimately, you should have an objective for your analysis, and normality is usually not the most important one. For the conclusion, I originally wanted to put a song here, but it is quite difficult for me to sing it, and it's about 4 minutes long, so I'll post a link to it here later when I have it uploaded. Anyway, I hope that I've made the following points clear. 1. When normality is assumed in common scenarios, z-tests, t-tests, and linear regression residuals. 2. Why normality is often a loose requirement in those scenarios, because you can't find truly normal data and close enough just works. 3. How to improve a linear model, getting better, more normal residuals. And 4. Input variables to generalized linear regression models do not need to be normally distributed, which, to be honest, I could have solely addressed and would have covered about 80% of all the online questions I alluded to at the beginning of the video. If you have any questions or feedback, feel free to leave them in the comments. This is my first video, so I'm doing a bit of experimenting. Although I have ideas for future videos planned, I'm open to hearing any suggestions for future topics. And don't forget to click the thumbs up if you liked the video, and subscribe if you'd like to be notified of future videos like this, or when I give my overly dramatic song uploaded. Cheers, and have a wonderful day.